Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is to continue working on our JSFX library that comes with a design system, some algorithms for things that you usually want to do in digital signal processing, and that kind of thing. Specifically, what we are going to talk about today is over here. We are going to continue talking about noise. We started this conversation last week, I think it was on Friday, and we implemented white noise and brown noise. I want to make some remarks about brown noise, fix a couple things that I learned that I know are wrong, and then we will talk about pink noise, how to generate pink noise, and maybe even what it can be used for. So let's backtrack. Let's talk about brown noise. I am going to load our effect. It is right here. This is us using the library to demonstrate what it can do. And right now I'm generating white noise and the master is muted. So I can make this fairly loud white noise. And then I have this spectrum analyzer here, and I want to configure it so that it has no slope. By default, if you load this spectrum analyzer, it comes with a slope. This is what white noise looks like on a spectrum analyzer. There are all these bands, different frequencies, and they all are at the same level. That's what white noise is all about. Now, let's switch to brown noise. And I am going to switch the slope to -6 or to 6, +6. And this is what brown noise looks like. It is equal amounts of energy, but the slope here is a 6 dB slope. So there is not really equal amounts of energy on this thing. There is a slope of -6 dB. Which means that on any given octave, there is 6 dB less than on the previous octave and 6 dB more energy than in the next octave. And Bo is here. Hey Bo, great to have you. I am doing well. How are you doing? And yes, we are going to talk about pink noise. And the method that we are using to generate brown noise is not to just take white noise and filter it. But we could, right? We could start with something. So let's turn off the slope for a moment. So we could start with white noise, which would be a straight line. And then we could filter it just like this, with a kind of a tilt filter of 6 dB. And that's relatively straightforward to do, actually. There are these very simple filters. We do have more sophisticated filters implemented in our library already, but you can do this kind of filter with a relatively simple filter, something called a one-pole or first order low-pass filter with a slope of 6 dB. So let's open the Wikipedia article, I think, for one-pole or first order low pass filter. And then let's find the difference in equation, that one. Great. So I'm not going to dive too deep into the mathematics of this, but in this case, any sample, this is Vn. It's using weird notation here. We haven't used really the V notation for samples, but the sample Vn is equal to the previous output. We usually use the letter Y when we were talking about these letters here, the V. When we were doing filters, we used the letter Y. So the output, in other words, the brown noise, is equal to the previous sample in the brown noise plus this lowercase v n. The lowercase vn, you can understand that as the signal you are filtering, so you can think of this as the white noise, and the capital V is the brown noise. So that's the difference equation for a low-pass filter. A very simple one, first order one. And a difference equation is how we have implemented all our filters so far. So you just take the previous output of the filter or the previous sample in the brown noise, and you add that to a source of white noise. And then you multiply these two by coefficients such that it's going to add up to 1. So you are doing some weighted averaging of the previous sample and the white noise source. So that's how you do a first order low pass filter. And we could just take white noise, pass it through this filter and get brown noise out. Let's take a moment to think about the way that we implemented brown noise. We did not use this formula. We did not filter white noise. We did something else. Let's dive into the code and I will show you. We do store the previous sample. And then this is the main line that makes everything work. So we take the previous sample and then we add a small amount of travel. So we learned last week that brown noise remembers the previous state and it's just moving around based on the previous state. The idea comes from Brownian motion, where there is a particle somewhere and it's moving around in space and it's moving randomly, but the particle doesn't teleport somewhere else. It's moving in space from here to there in relatively small steps. And that's what we are doing here. We are taking the random value and multiplying by this travel amount, which is a relatively small number. So we are not just jumping anywhere. The next sample is not just completely unrelated to the previous one. It is the previous one plus a small amount of travel. So we implemented this based on the physical concept of brown noise. But take a moment to realize that the two are actually the same thing. Let me split the screen. So Vn is our brown noise, so the current sample and the previous sample is Vn and Vn minus 1. And rand is white noise. So this lowercase vn is the source of material that we are filtering, the white noise. So we implemented this formula reasoning about Brownian motion. But we could have reasoned about taking white noise and filtering it, and we would have arrived at exactly the same equation, exactly the same result. I find that endlessly fascinating. There is this correlation. In fact, you can think of brown noise as filtered white noise, or you can think of the Brownian motion. It amounts to the same. And even if you think about it, the physical interpretation of a particle moving in space kind of makes sense. If a particle is teleporting everywhere, that's a high frequency movement. It is moving very fast. And Brownian motion is just a high cut or a low pass filter on that movement. Cool stuff. I find that fascinating, but there is no change to the code that's required by this. I just wanted to mention this because I thought that was interesting. Next interesting thing is I was looking at how other people implemented brown noise. And I swear that I did not check this before our stream last week. We calibrated this by hand looking at the spectrum analyzer tilt. And then I looked at how Audacity implemented brown noise. And check this out. They have exactly the same constant. Now, this is commented out because of a bug. that we have in our code and they don't have in theirs, and we are going to fix this. But the cool thing is that they did the same thing that we did. So they implemented the thing in about the same way. They have some source of white noise that they are essentially filtering. You can reason about this however you want. You can think of filtering white noise. You can think of this as modeling Brownian motion. It doesn't matter. So they are essentially doing the same. But this factor here is something that they tuned by hand, and we did that as well, and we arrived at the same constant, and I find that amazing and incredible. I mean, look at this, exactly the same value. But there is a wrinkle. This value is related to the sample rate. This value, the travel amount, is a multiplier that we apply to the previous sample, or that we apply to the random value that we are going to add to the previous sample. So in essence, the travel amount is how much the particle can move around. And the issue is, if you increase the sample rate, right now when I'm testing and in everything that I do, I use 48K. But if you increase the sample rate, then this travel amount will represent less motion. It is going to move more slowly because you can only travel so much to the next sample, but that next sample is going to happen sooner. Now I'm getting confused. I'm not sure if it's going to be slower or faster. In any case, it's going to be wrong. That's as much as I can tell you. This value that we tuned by hand has to do with the sample rate. If we increase or decrease the sample rate for that matter, this value is going to be wrong because it's going to let the particle move further or not as far as before. And that will have an influence on the frequency. And then we will not have the 6 dB slope that we are looking for. So the fix for this is relatively straightforward. They do some more stuff here with leakage, and that has to do with how the first order filter works. They are not necessarily modeling the motion, they are more thinking about filtering white noise. But the essence of the thing is that this is the sample rate, this is the travel amount necessary for this sample rate. So how about I divide by the sample rate, or actually divide by my current sample rate and multiply by your sample rate. By doing this, I'm converting the value from my sample rate to your sample rate, and then this value is going to hold even if your sample rate is not the same as mine. Now, of course, because my sample rate is what it is, the value is going to be the same. So this is 48,000 and this is 48,000, so these two values are going to cancel out and we'll not have the right slope. Or we will have the right slope, but we are not really changing anything. So maybe I'm thinking here, maybe what I need to do is to actually make the error occur and then I'll see if this works. Because either I have to do this or I have to do that. I'm not really sure which, and it depends on that logic that I'm having a hard time wrapping my head around. It's either that when you increase the sample rate, I need to make the motion slower or faster. Let me reflect on that for a moment. I think that if you're increasing the sample rate, you have more samples to get somewhere, so you should move more slowly. So I think it should be this. Or actually, no. I think it should be that. But we'll try to make the error occur and test it for ourselves. So let's comment this out for a moment and try it experimentally. And Bo is saying a higher sample rate will give you wider bandwidth, so it will filter less. The samples will move more. So do you think that I should be multiplying and then dividing, or dividing and then multiplying? Also, probably this is something that I could extract, because right now this would be computed over and over for every sample. I think that I probably can extract this into a constant somewhere. So how about in the init block, I have noise brown travel amount. And Bo is saying, I would use the tau formula. I don't know what you're talking about, Bo. What is the tau formula? And everywhere where I see the travel amount, that's no longer a local variable. And then naturally I don't need this line. And that's just a constant travel amount, blah, blah, blah. Yeah, I think that this refactoring is successful. Oh, so Bo is proposing to use a completely different formula with a cutoff and everything. I don't think we need that. I think we can get away with just this value being well calibrated. And probably if you put a cutoff frequency of about half the sample rate, you will end up with a number similar to this. In fact, why don't we try it out? Let me dive into here. I just want to have something where I can plot some values. So if I look at the exponential of -2 times pi times, I want a cutoff that is, I want to say about 0, right? Because it's a low pass filter, so I want the cutoff to be about 0, and then I will see the slope throughout the frequency spectrum. So I think it's like 0 at this point, divided by the sample rate. And I do realize how silly this is, because the whole thing is just going to be 0. But the exponent of that is equal to 1. So yeah, I don't think that's exactly what I should be using. I need a value that is much, much lower. Alternatively, if I think about it the other way around and say that the cutoff frequency is half the sample rate, then I will end up with a number that is close to 0.05. So maybe that's what I should be using. That's actually a smart idea. It's even better than what I had in mind, and it is completely dependent just on the sample rate. Now, it is silly that I'm multiplying by the sample rate and dividing by the sample rate, isn't it? That's the same value. Oh, but that value is now dependent on the sample. It's not dependent on the sample rate anymore, which is the issue to begin with, as far as I understand. So no, I don't think that's going to be a solution. Maybe I am misunderstanding something. There is that's the same one you used for exponential moving average RMS, remember, and you can definitely simplify it. It's made to work from a manageable slider value, not a set value. But in our case, we do know what we want the cutoff to be. We want it to be -6 dB across the spectrum. So yeah, I'm going to try to make the issue even occur, and we'll try to see if we can make the issue occur. Right, so right now we have all this setup. I can come here and change my sample rate, but not for my audio device. That is going to mess up the whole stream. So how about I try to change the sample rate of the project to be something like 96K. And I will save that. And then I need to double check that. Yeah, it seems like this stream is not affected. I hope I didn't mess up my other REAPER instance that is processing my audio. And look at that. I think that we are no longer with the right slope. Oh, it's not -6, it's 6. Oh, would you look at that? It seems like it's not an issue. It did affect the level though, and that is interesting. Can I resize this? Great. So right now it is with a slope of 6. And I'm going to reload the effect because I did that quick refactoring. Extracting a constant instead of computing it every time, which I think still holds, even if we decide not to compute anything. If the constant is just 0.05 and it's hard-coded, still think it makes sense to have that as a constant elsewhere. Yeah, but that seems to be working just fine. And we are at 96. Okay, oh, and my voice sounds really weird now. Yeah, probably because of that change. Gonna try to fix that real quick. I think that maybe the best way for me to fix this is to restart the whole thing. So you will hear me in a moment. Hello, I am back, and I think that my voice no longer sounds weird because I made sure that everything is back at 48K. My audio interface is at 48K, Reaper is at 48K. I'm not gonna play around with the sample rate in the stream again. And this is the instance where we are going to play around and drop the effect back in. Yeah, much better. Great. So I could not make the error even occur, so maybe I don't need to fix it. And if I don't need to fix it, then maybe I will, or maybe I won't extract this constant. Yeah, I think I'm not going to extract this constant. Just discarded those changes. And yeah, so in theory, the brown noise is not going to work with other sample rates, but because I cannot reproduce the issue, I'm not going to try to fix the issue. I will let the issue manifest itself, and if someone complains, then we'll do something about it. Right, let's move on to pink noise. So to discuss pink noise, I want to refer back to this lovely article that I talked about last week, and it is worth a read. It's not mathematical at all, relatively straightforward to wrap your head around, and it talks about fractals, talks about music composition and algorithmic music composition, which is a topic that interests me, and it does talk about different kinds of noise. And they are not necessarily talking about how to generate pink noise, but in the process of preparing the article, the author asked if one of the researchers could come up with an algorithm to generate pink noise, and they came up with something. And that's pretty much something that you can use to this day, which is like amazing if you think about it. So in this figure, we can see white noise is just completely random, and Brownian noise, so it is the previous sample plus some small variation. And this is pink noise. It's in the middle. It's not as random, but it's not so ordered either. And the initial thought is, well, if we could filter white noise to generate brown noise, how about we filter white noise to generate pink noise? Yes, that's something that you can do. And there are even filters that were designed specifically for doing that. It's not such a simple filter as the filter we used for the Brownian noise, but it more or less looks like this. So this is the filter in black, and it's made up of some filters, collection of filters that are pretty much the low-pass filter we used for Brownian noise, but they are multiple filters and calibrated so that they overlap in this way and they add up to this almost straight line. It's not exactly straight line. And if you needed pink noise to calibrate some sophisticated and delicate medical equipment, then maybe this would not be ideal, but for our purposes of making music, should be good enough. So yes, you can just use this filter, and the coefficients for the filter are somewhere in this article. You can just copy and paste the code and it's gonna work, or you can even go to the implementation in Audacity. These are the coefficients. So they are taking white noise, they are doing a filter, and they are coming up with pink noise. And that's a valid strategy. But that's not what the person collaborating to write this article did. They came up with something much more interesting. And it's not going to generate, again, exactly pink noise, right? It's not going to be perfect pink noise, but it's going to be close enough that we will call it a day. And the idea starts with slowing down white noise. So what happens if I take white noise and I play white noise at half the sample rate? In other words, I'm generating white noise, but instead of generating a random sample every sample, I generate a random sample and I repeat it on the second sample. Then on the third one, I generate a new sample. And then on the fourth, I repeat the third. So it's a simple sample and hold of two samples. Random equal to the previous one. Random equal to the previous one, and so forth. What happens in that case? Something for you to think about while I am reading the rest of the chat. So, wouldn't taking 0.05 times 48,000 give a number you can work from? Yeah, the problem is I don't know if I should make 0.05 smaller or bigger. My intuition is that I should make it smaller when you increase the sample rate. So I would be multiplying by the new sample rate, no, multiplying by 48,000 and dividing by the new sample rate. But if I am wrong, I'm gonna make matters worse. So we couldn't reproduce the issue. I'm not gonna try to fix it. But yeah, I think you understand what's going on, right? Right, so what happens when you take white noise and you slow it down? Let's actually test this out. I'm going to go to the implementation of pink noise. And let's write this down. We currently have some data structure for Brownian noise. Let's create a data structure for pink noise. And right now it's only going to remember the previous sample. That's fine by me. And then we don't need the notion of travel amount. We do need the notion of the previous sample. And oh, we also need something else. We need to know if we should repeat previous sample. And to begin with, we're going to say that false. we should not be repeating the previous sample. We should be computing a new one to begin with. So it starts with false. Then we get a hold of the previous sample, or actually we can divide this into parts. Let's start by copying this and doing that. And then we can check. If I should repeat the previous sample, then I just get a hold of the previous sample and I output that. It's kind of silly for me to use a variable for this, so I'm going to do it like this. If I should repeat the previous sample, then return the previous sample. Oh, no, it's not that simple. I also need to reset the variable. So let me backtrack for a moment. I'm going to do it like this. So if I should repeat the previous sample, I am going to repeat the previous sample, but I am also going to say that I should not do it the next time around. That's this line. Then, in the other case, if I should not repeat the previous sample, it means that the next time I should repeat the previous sample. And I also need to take a hold of the current sample. And this is just going to be essentially white noise. So I think I'm just going to call that. And then the current sample is going to be stored just like this. And then I return the current sample. And all of this I can get rid of. Let's review this. Data structure, 2 fields, previous sample, and should repeat previous sample. To generate pink noise, I need a data structure. And then I get a hold of the parts of the data structure. I first check if I should repeat, and if so, I get a hold of the previous sample and I output that, but I also flag that I should not repeat the previous sample next time. Otherwise, I generate some current sample, I put it in the data structure, I set the flag so that it should repeat the next time, and I return it. I think that is correct. So now let's reload the plugin and see what it looks like. And this time we want a particular slope of -3, but let's go with 0 for now, because we are essentially working with white noise so far. So white noise on the spectral analyzer looks like this. And pink noise, well, it's not really pink noise so far, it's only white noise slowed down. That does not look right, does it? Let's put an oscilloscope to really understand what's going on. That does not look right. I made some mistake. Let's review. I'm betting that there is a typo somewhere. Oh, I added this to the brown noise data structure. That's the mistake. Well, that's one mistake anyway. Okay, this is what, well, let's increase the gain. This is white noise. Let's switch to pink. and there is still a mistake somewhere. You're still getting only ones. Yeah, let's continue debugging this. Is there any other occurrence of brown where there shouldn't be? No. I don't need the travel amount variable. That's not a mistake. Is this false and true correct? It seems to be. I cannot spot any mistakes, so I'm going to commit what I have and I'm going to start playing around with the code, putting some debug statements here and there. Let's see if this is changing. It should be. I don't think it is though. Interestingly enough, the debug variable doesn't even show up. And now that's about as crazy as I want to go. Probably there is some other issue going on. Yeah, the debug variable is not even showing up. So it seems like we are not even generating anything to begin with. That is just too crazy. So we are going to take more low-level steps. Are we even getting in here? How are we using this function? Are we even using this function? No, we are not. We are not calling this function. So yeah, I wonder why we are getting any output at all. Yeah, we forgot to call the function. So we need to say sample noise is equal to, well, essentially this line, except that instead of brown, it's going to be pink. And we do need to find where we are creating the brown instance so that we can create a pink one. Right, and then we don't need any debug here. Let's see if I changed anything else that I don't like. Doesn't seem like it, so dropping in the effect again, moving to pink. What are we getting? Okay, we are getting something. Great. So right now, this is what white noise looks like, and this is what pink noise so far looks like. Isn't that interesting? Let's look at this in the oscilloscope. Really close. See, I think that these are two samples. I don't know how to tell actually if this is one sample or two samples. It should be two samples. Oh, I think there is a way for me to move around with this. Well, I know that it comes about here in the pink noise. So let's remove the hold, put this there, change to white. No, it doesn't seem like it's holding two samples, does it? Yeah, I think there is something else. That is wrong. Right, so let's do the debugging that I wanted to do in the first place. So debug equals current sample. Right now debug is 0. Let's switch to pink, make it a little bit louder, and this value is changing. All right, that's okay. And repeat debug repeating, and or actually this is debug new sample, and this is a repeating sample. And both of these should be changing. And they are changing. So it means that we are outputting 2 repeated samples. But for some reason the oscilloscope is not fast enough to get it. I don't know. I wish there was a way for me to see how many samples is in this line. I'm not sure if it's 1 or 2, and I don't know how to use... There is a way for me to move around with this, but it doesn't really work all that well. I don't know how to use it. I am pushing it around and it's not doing anything, and now it's just acting weird. I am inclined to say that there is only 1 sample on this, guys. And there is something weird that is happening. I see only 1 channel. It seems like both channels are completely correlated, and that is not what was supposed to happen. Or is it? How are we using this? Oh, hanging there. We have only 1 instance of pink noise and brown noise for all the different channels, so we are looping over the channels, but we are reusing the same instance every time. That's not going to make things happy, is it? We need different instances of pink and brown noise per channel. That's a very primitive mistake right there. So it seems like I am right in my interpretation. The pink noise is putting the same sample out twice, but it's doing that on the left and right channel, so I don't see it here. Oh man, let's fix that. Print to an audio file and zoom in on it with the regular window. Yeah, we can do that, but I think we have this mistake already that we need to fix, and then we may need to do that. And I think that the reading on the oscilloscope was right. It was just me in disbelief because I didn't want it to be true. Right, so let's have arrays for this. Great. So now we have 1 brown and 1 pink noise per channel. Let's move down to where we are using this. And then the white noise doesn't need that, but the brown noise and the pink noise will need that. So the instance, it's not really the instance anymore, right? The array is an instance variable, but a particular one is just a sample noise, brown and pink. So I'm going to leave this, and then instance noise, and then sample channel. And I need to change. Oh, look at that. I will be able to do everything using cursors, and cool. Visual Studio Code tricks. Oh, not quite. I think I have it. Sample noise brown, instance noise brown. Well, not instance. Sample. And now I think we have different guys for different channels. We could just make it mono, but yeah, whatever. Yeah, let's reload this real quick. Co-slope. We are getting stuff. And now I am getting the result that I wanted in the first place. Let's look at the oscilloscope. Let's hold. And then, oh yeah, that's brilliant. Now we can see 2 samples. Great. And how can we tell that it's 2 samples? What am I supposed to do with this button? It doesn't make any sense. If I scroll up and down, it doesn't really work. If I scroll left and right, then it kind of works, but it's super weird. Super weird, but it's one sample, it's going left one sample at a time. So now I can tell that there are 2 of these samples, and they're multi-channel because I see left and right, or left and right, who knows? Whatever. So now I have fixed all mistakes, it seems. Let me commit what I have, and then we can talk about what we see in the spectrum analyzer. Right, so all of this was so that we could look at what happens to white noise if I sample and hold for a moment. And look at this, now the correlation meter makes more sense. Before the correlation was 1, and a correlation of 1 indicates that it's a mono signal. And it should be a correlation of 0. The left and right are completely uncorrelated noises. Right, but we are looking at white noise, sample and hold once. So look at this, right about here, where is half of our frequency spectrum that we can represent, we start seeing this decay. Essentially what we are doing is we are filtering out the high frequency because we are not allowing things to change as fast as they were before. So in essence, if you sample and hold white noise, first of all, it looks like white noise. Remember that this slope is 0 right now, so it looks like white noise in almost the entirety of the spectrum. And this is not really something, this decay here is not really something that they talk about in this article because it's from 1978 or 1977. People were not thinking about sample rates back then. They were mostly doing analog stuff. I mean, there was a lot of theory around sample rates, but they were not using DSP a whole lot. They were definitely not coding real-time plugins in REAPER. So they don't really talk about this, but it intuitively makes sense. We are not letting things change as fast, so we are cutting off the high frequency. In essence, this kind of looks like the slope you would find in the series of filters necessary to create some pink noise. And you may be wondering, isn't there a filter that does a 3 dB slope? And the answer is not quite, not a simple filter anyway. Usually filters like to be 6 dB, 12 dB, 18, 24, and so forth. Very simple filters don't like to have a slope of 3 dB. So that's why it's not as trivial to generate pink noise as it is to generate brown noise. Right, so this is what white noise looks like if you sample and hold for 1 sample. What if you sample and hold for 2 samples? Right, you generate a new sample and then you emit that sample on the next one and on the next one. And only then you generate a new sample and you emit that one for 2 more times and you repeat that idea. Well, you are letting things change even more slowly. You are cutting off the high frequency changes even more. So I don't think I am going to implement it because I don't feel like it, but I think that this slope is going to go lower and lower and lower. You know what, let's implement this real quick because I think it will come in handy for the real implementation of pink noise. So let's implement that. The should, repeat, all of that is going to need to change. So I'm gonna call this the repeat count, and it's going to start with 0. And if the repeat count is equal to 2 this time, and then the repeat count plus, well, if it is equal to 2, I'm going to 0 it again. Otherwise, I'm going to increment 1. So now we have this number we can play with. Let's think about how this number even works. It starts with 0, and then we generate a new one. No, this is incorrect. Let's reverse the logic. If it's equal to 0, then no. Let's not reverse the logic. Oh, yes, let's reverse the logic. Okay, I got my head straight around this one. Great. So if it's equal to 0, then generate some white noise and reset the repeat count to 0. Because I have not repeated this yet. I have only output this once. But how do I wrap back? Oh man. Such a simple logic, but give me a minute. Yeah, the first time around I want to go this path. So if the repeat count is 0, generate something new. And then it is kind of silly to set the repeat count to 0 because the repeat count is 0. So I don't need to do that. But then I am going to keep coming around on this, right? Oh man, this logic is so simple. I just want to repeat this sample for so many times. Oh man, let's do this. The current repeat count is that. If it's equal to 0, it's the first time around I want to generate some white noise. I'm going to store this for later. And it's no longer even the previous sample, it's just... I'm gonna call this like the current sample. Or even the sample to repeat. Right, okay. The repeat count starts at 0. I know I'm in a loop. I keep saying the same thing. It's very hard to think about this sometimes for me. I don't know if it's like this for everyone, but I have a hard time thinking about all these edge cases and all this silly logic. Right, so the first time around, I want to generate some white noise. I want to store it for later, and I want to return it. But I do want to increase this repeat count. How about if I do this? It's kind of silly. And I do need to start with -1, so I don't start with zeros. I actually generate something on the first sample. And this works. It does look silly. But whatever. I think it's okay. No, it's not okay. It looks terrible. And also I need to do something else with the logic. Right, so repeat count starts with 0. I generate some white noise. I store it for later. I output the current sample. What if? This is probably going to help me think. If I do this, I just rename the variable. Now these two have the same output. So I can move this down. And what that allows me to do is to manage the repeat count in a single place. All right, let's go over this again. Nothing too interesting going on here, but I think that I need to start with a 0 on the repeat count. And then I get a hold of the repeat count. I check if it's 0. If it is, then I generate some white noise. And I store it for later. Otherwise, I just retrieve it. And then I increment the repeat count. I manage the repeat count. I wrap it around if necessary. I store the repeat count that I had changed. And then I output that sample. Okay, so it's going to start with 0. Then it's going to emit a new sample. It's going to go around. It's going to be 1. It's going to emit that sample. It's going to come around. It's going to be 2. It is still going to emit that sample. And then it's going to wrap around. So this time it's going to output, yeah, I think I did it. It's going to output the same sample 3 times, and then it's going to switch around, output the new sample 3 times. I think that's what it's doing. Man, that was so hard. I felt pain. That doesn't look right. There is a huge DC offset, and then it's essentially white noise and very low. And what does the oscilloscope say? Well, it does seem like I'm getting sort of correlated answers between correlated samples between left and right, and that's not a happy day for me. What could be wrong? I don't know. I will need to write some debugging stuff. I don't even know what to debug here. I'm going to debug the repeat count. Should be going up, right? Well, it should be going between 0, 1, and 2, 0, 1, and 2. Stuck at 1. That is probably bad. Oh man, I forgot to rename this. Okay, no other occurrences. Okay, we are back to a working state. So this is 2 samples of hold. is it outputting 3 times the same sample or just 2 times the same sample? Just 2 times the same sample. So it's exactly the same as before. If I change this number to 3, oh, that's different. That does look different. And now we are outputting the same sample 3 times. Okay, I was off by 1, but whatever. The point here being, the more I increase this number, the more this notch is going to come down on the frequency spectrum. So let's make it like 5. See? Now, what if we have like 100? Let's play around with this for a moment. Right? Nice calm filter there. Look at that. So many samples the same before they are allowed to change. 100 samples that need to be the same. But if you look at it in the grand scheme of things, it's not that bad. Right. Still looks like pink noise. That's what I mean. Doesn't look that bad. Still looks like, well, white noise, I guess. Still looks like noise. Right, cool, calm filter. Okay, so let's put together some ideas. We want to have pink noise is essentially a 3 dB slope. Let's look at this with a 3 dB slope. We want this to now be a flat line. It's not too bad. This is approximating a flat line. And we know this notion that if we sample and hold, we are doing a low-pass filter. But we don't want just one of them, like we needed in the brown noise. That was the easier case. We need a couple of them. This is the insight on this paper from 1977. And that's the brilliant idea of how to generate pink noise that we can use in our code. The idea is we are going to have not one source of white noise that we filter. We are going to have a couple of these. One source of white noise that is updating every sample, one source of white noise that is updating every 2 samples, one source of white noise that is updating every 3 samples, and that sort of thing. Not exactly 0, 1, 2, 3 samples, okay? It's just, I'm going to add all these sources, and they're going to contribute. So this one is going to contribute, for instance, this much in the frequency spectrum. Another one was contributing the thing that we saw before with 1 notch, and another one is contributing more or less a flat line. But if you add all of this together, they're going to make up a slope of 3 dB. Isn't that a clever idea? It's kind of amazing, really. And the rate of change of these samples needs to be, one is going to change every time, the other is going to change every 2 samples, every 4 samples, every 8 samples, 16 samples, 32 samples, and so forth. It looks like this. There is this other article here that I was showing you before with the graph. It kind of documents everything that people know about how to generate pink noise since the early 2000s. And what we are interested in particularly is a little ASCII art this. So you can think of these lines as the different white noises, and the vertical, the rolls. So lines are the different sources of noise, and columns are samples over time. Time is going from left to right. And every time you see an X, you have to update that source of white noise. So 1 is being updated almost every sample. There is an extension of this. So yeah, one source is updated every sample. One source is updated every 2 samples, one source is updated every 4 samples, one source is updated every 8 samples, 16 samples, 32 samples. And I think that about does it. So you need 6 layers of this to make it work across the frequency spectrum. That's the idea. So we can generate pink noise by having multiple sources of white noise that are updated in different rates, and we add them together. Because every source of white noise that we only update every so many samples is a source of white noise that has been filtered, low pass filtered to some extent. And if you add all of this together, they are going to make a curve that resembles something like this. It's a bit bumpy, it's not exactly straight, it's not a perfect 3 dB slope, but it is good enough. That is a weird and clever idea, I think. And there's something else to be talked about, and that's this notion of 1 over f. If you go like to the Wikipedia article for pink noise, and in many other places, pink noise is referred to as 1 over f noise, and brown noise is 1 over f squared noise. The idea is, think about the frequency spectrum here on this graph. Oh, Mo has a question I'm going to try to answer before I explain why it's called 1 over f noise. How about a regular 6 dB filter that gets an original signal mixed in to achieve a 3 dB slope? Okay, what you're talking about, if I understand correctly, is you have a source with 6 dB slope. So right now the graph here, it has a 3 dB slope, so we see a little bit of a slope here. That's brown noise. Add that to another source of noise. Oh, but I don't pass through my source of noise here. So yeah, I have brown noise. I'm going to add something else instead of my own effect, because my own effect doesn't pass the original audio through. I'll put this white noise generator. As far as I understand, it passes through both things. So you want to pass the dry sound. The dry is brown. Let's put it at -12. And white noise. So if you add brown noise, 6 dB slope to... Take white noise. Okay, let's do it like this. This is white noise. And we have no slope. Great, white noise. Now, add to that equal amounts of a 6 dB slope. That's brown noise. I think that's your idea, right? Doesn't really work, does it? It doesn't work in a way that kind of surprises me, but I guess it makes sense. If we don't have any slope, then in this graph in particular, because of the axis that we are using and the range that we are using, it dies off very quickly. So if you add that to white noise, it doesn't make a lot of difference. It does make a bump here. It doesn't make a lot of difference across the spectrum. That kind of makes sense sonically as well. When I hear white noise, it's like in your face. And if you have a little bit of brown noise behind that, you're not going to notice it. But we can play around with the mixer here, try to get more of this dry sound and less of the white noise. And try to get somewhere in the middle. Let's see if we have a 3 dB slope. Nope. Yeah, I don't think it's possible. I don't think it works. Even if I play around with this, the more I remove the brown noise, the more this slope goes away. And if I leave the brown noise and I start adding or subtracting white noise, can never get it straight. There's a big bump in the middle. Yeah, are you sure it's adding though? Yeah, it is. It is adding. Use the mix knob on the plugin window, more or less what I'm doing. Isn't that gray noise with this mild curve? Not too far, I don't think. Yeah, as far as I understand, gray noise is a bit more complicated than this. It's not just this mild curve. It has to do with how humans perceive noise. So there is a little bit more detail in the curve, but it's not too far. But you can see it's not possible to just mix in these two signals. And it makes sense, right? If you think about it, you have something that is flat, something with a 6 dB slope. How can you add these two things and have them turn around? They're not going to turn around. They're only going to add up or not add up. But it's not going to change the slope. So we end up with a 6 dB slope. Let's put a 6 dB slope and look at this. So right now I have a lot of white noise. If I remove it, that should be brown noise. It's flat. And as I add white noise, goes up. Yeah, right. So what we want is that strategy that I was mentioning, adding up all those white noise sources, updating at different rates. But it is interesting because white noise is a fractal. If you slow down white noise, it still looks like white noise. And in the digital domain, there is this whole problem of the sampling frequency. If you only update the white noise every 2 samples, you are essentially decreasing the sample rate to half. So there is the Nyquist frequency, there is a cutoff in the middle. But if you don't take that in account, you can have the rate of change of the white noise and it still looks like white noise, sounds like white noise across the spectrum for the most part. Well, didn't work, but gave me an idea for a mild slope EQ. Yeah, well, essentially it's, I guess, a one pole. Yeah, it is a first order low pass filter added to the original source with some dry signal. Yeah, that's what it is. And it can be useful, yeah, because many people do like the smile curve, and naturally you can do that with any sort of EQ. Just take a band, make it very wide. Looks more or less like this. Not too far anyway. Right, so white noise is a fractal. The idea for pink noise is we are going to add a bunch of these. What is up with 1 over f and 1 over f squared noise? Coming back to the spectrum analyzer, think of this as energy. So there is the frequency on one axis, and then there is the area under the curve. That's the amount of energy in that space between the frequencies. So this is literally just going to be an area under the curve. So there is the space in one axis, that's the frequencies, and the space in the other axis, that's the intensity in that part of the frequency spectrum. So if you multiply the two, you get some amount of energy. And what people say when they're talking about 1 over f is the amount of energy you're going to get with something like white noise. So let's put a slope of 0. And get us some white noise. So with a slope of 0 and some white noise, you're getting the same amount of energy across the spectrum. But with something like brown noise, you are not getting something with equal amounts of energy across the spectrum. You are getting less and less energy as you go up the spectrum. And if you multiply, remember that this is a logarithmic scale, okay? We are going from 1K to 2K here and from 100 to 200 here, and it's the same amount of space on the screen. But this is 100 hertz and this is 1000 hertz. So the space under the curve is going to be very different here. And it is related to the frequency. The higher the frequency, the less the intensity of sound. So you end up with an amount of power that is 1 over f, or the amount of energy is related to the frequency. The amount of the height of this line here is related to the frequency, in a way that the higher the frequency, the less the power. So if you think about it with the formula 1 over f, it is just saying that the amount of energy is inversely proportional to the frequency. That's why it's called 1 over f noise. And in the case of brown noise, it actually is the square of the frequency. So in 1K, we are going to have much, much less energy than in 100 hertz. And this relationship is a square. And with that, let's put again the slope to 3 and try to get some pink noise to work. Let me move to pink. Right now we have this weird curve here. And to make this work, we are going to need I think we are going to implement this version. So we need 5 sources of white noise that update every so often, and we need 1 source of white noise that is always updating. Let's take care of this one first because it's easy. There you go, that's taken care of. Now we need 1 source that updates every so often, and another source, and so on. So how about we have in this data structure an array? Yeah, I think I'm gonna go with an array for this. So we don't store the previous sample and the repeat count. I think it's time for me to commit this so I don't lose it. I'm going to revert and commit what I have, because I fixed some mistakes, didn't I? Yes, I did. Right, okay. So we no longer have 1 sample to repeat and a repeat count. No, we just have white noises. And we do need to define that there. So some pink noise is just a data structure with a single field called white noises. That field is going to be an array. Bo asks if this is how tilt EQ works, stacking different slope filters. I don't know how tilt EQ works. I do know that there are 2 kinds of tilt EQs. One kind has a shape sort of looks like a high shelf and a low shelf, and when you change one, the other changes as well. So it let me put the higher Q on this, trying to reproduce what I know as a tilt EQ with re-EQ is not gonna make me happy, is it? So it's more or less like this. There is a little bit of a curve to that. Let's remove that, make it bigger. It's more or less look like this. And if this is the kind of tilt EQ that you're looking for, then I am sure you can do this with just a stack of filters, because that's exactly what I have here in re-EQ. But there is also a flat line tilt EQ, and that I don't know how it works. I don't think you can do that with just a series of EQs. You do have to design that filter specifically for that purpose, but I don't know how to design such a filter. Haven't got to that yet. Right, okay, so This is now an array of 5 different sources of noise. And we need to store something else, really. We need to store something that I'm going to call a counter. The counter is going to start with 0. Because there is a clever technique to determine which filter we need to update. So first of all, note that for every sample, there is this source of white noise here that we can ignore. In fact, I'm going to ignore it because we have already taken care of it by doing this. So I'm just going to look at this. Note how for every sample, for every column, there is only one X. There is only one sample that we must update. So it's just a matter of determining which sample we need to update. And it's going to be one of the 5 samples in this array. The clever technique to determine which sample to update is to have a counter and to look at the number of trailing zeros on that counter. So we're going to update this counter 0, 1, 2, 3, and so forth. But we are going to interpret that as a binary number, and we are going to check how many zeros, how many leading zeros, trailing zeros, I forget, zeros at the end, least significant bits, how many zeros there are. And if there are no zeros, then I update this guy. If there is 1 0, I update this guy. If there are 2 zeros, I update this guy, and so forth. So that's how this is going to go. We are going to do some bit twiddling for this to work. Isn't that cool? Right, so we have our white noises and our counter, and we are initializing this array with a bunch of zeros, and that's all right. Then all of this, I think, is just going to go away. We need some white noises and counter. And the counter here is going to resemble our repeat count. This variable is going to tell us when to update the source of white noises. Let's get a hold of the white noises as well as the counter. Oh, and there is one more thing that I need to store. I need to store the previous output. That can be a 0. Why do I store the previous output? It's similar to the trick we used when calculating RMS. We are going to store what was our previous output, and we are going to use a difference equation. Because in theory, we would have to add up all the 5 lines of white noise. We are only updating the white noise every so often, but we do need to, all of them contribute to the output. We do need to output all of them, so we would need to add all of this up. But because of this clever arrangement, we only need to update one of these at a time. So we can take our previous output, subtract the previous value that was in this line of white noise, add the new value we are generating, and that's our new output. So we can do less work, which is cool. And all of this is going to be independent of this source of white noise. I don't want that messing with everything else. Right, so we do have the white noises, we do have a counter, and we do have the previous output. Great. Now, when we want to generate white noise, we want to essentially get a hold of all of these. I called something previous sample before, and now I'm calling it previous output. Yeah, whatever. So I am deconstructing the data structure, all right. And then I need to find which of these lines to update. I'm going to have a local variable called white noises, or even noise white noises index to update. And I will want to update this counter. And I will want to store that update. Right, okay, so deconstructing. Then I need to determine this index to update. And now I need to count the number of zeros to the right of the number. So I will have a number like 5. I will need to deconstruct that into a binary number. Yeah, so that's 2 to the power of 0, 1, 2 to the power of 1, 2, and 2 to the power of 2, 4. So that's 5 in binary. And then how many trailing zeros do I have? In this case, I have 0 trailing zeros. If I had something like 6, then I would have 1 trailing 0, and so forth. How can I count this? I can have a while loop with the condition that I will need to look at my counter and I will end bitwise and, so that's why there are no 2 ampersands, just one bitwise and 1 move to the left this many times, and that should be equal to 0. That means that this amount of digits is this amount of digits to the right are zeros. I think I got this right. We'll check. While that is the case, I will want to update this and add 1. That's going to be my index to update. We are going to revisit this logic in a moment, but let's continue with this real quick. So I will want to update something, but first I have to update the previous output. I will have to say the previous output is equal to the previous output minus, or you know what? I can just create one white sample. My white sample is going to be what I'm going to store somewhere. Okay, so I am now working on this formula. My previous output minus I actually need to store the data from this. Not to store, I need to grab it. Add the place where I need to update, which is this. Plus my white sample. And I need to go there and store my white sample. Then I update the counter, I store the counter, I will need to store this, I am already doing. Can move this down. I will need to store my previous output. And I can get rid of a bunch of things that no longer make sense from this downwards. And this is no longer the sample to repeat. This is now essentially the previous output, which is kind of a silly name. But it is what it is. And I think this is it. So let's review this. Pink noise has some white noises, a counter in the previous output. I don't really think I need this local variable. Can do all of this in one pass. And I'll put some spaces. So we are deconstructing the original data structure. That's right. Then we generate some white sample that I will need to update. Then let's dive into this logic of counting zeros. Wonder if I should extract this to some auxiliary function. Maybe it will be useful in other places. Maybe not. I don't know. Let's reason about this part. It's probably the core of the whole thing. So the index to update is a local variable. All right, it starts with 0. Then while the counter and the result of this I think there is a mistake in this thing. Yeah, I will revisit that. I'm pretty sure there's a mistake there. So take the previous output, subtract what was there, and add the sample that I'm coming up with. Maybe I can write it this way. No. I could, but I prefer it like this. Then increment the noise counter. There is some bookkeeping that I need to do here. My noise counter, if it is equal to a certain number, I will need to say that my noise counter is equal to 0. I need to wrap it back around. So how do I figure out this number? This number is, well, I'm going to update this guy. And when I update this guy, I want to reset the counter because you can notice that this pattern here on the right is exactly the same as this one on the left. So I could just let this counter grow and grow and grow, but I think it's nice for me to wrap it around. And I want to do this when I have reached 1 to the power of 5, I think, or 1 moved left 5 times, I think, and then this became sort of a magic number that appears in 2 locations. So I think I'm going to extract that. The magic variable for brown noise is used in a single location, a single function, but this one is used here as well as here. So I am going to say that there is a noise pink size, or maybe even white noises size, but it's not part of the data structure. And I made a mistake. This should actually be there. Then I update the previous output, which has been computed here. I update the data. I want to follow the same order. So updating the data with the white sample in the right location. Great. Then I update the previous output as computed. So essentially, I'm now just storing stuff. And the counter, I want to follow this order. So white noises data. Then counter, previous output. And that I don't need anymore. That is going to be part of the output. There you go. Yeah, I think this is right. So all we have left to do is figure out if we got this right and if we got this right, which I think we got wrong. But to debug that, I think I'm going to drop a test effect here so I can play around with some JS effects. You can see me just playing around with formulas and mathematics here. So if I do this, I think I expect to see out a 1, and it is a 1. If I do this, that's a junk value. I wish I didn't have to have a special case for this logic. I think it's kind of hacky, but I think this will do. I think this is going to overshoot, and then I fix it. Let's test this with the numbers we played around with before. So I know that, for instance, 5 and 1 should be 1. It is. That should still be 1, and it is. And that should be false, and it is. Now for the number 6, that should be true, and it is. And that should be false, and it is. So I think I got the logic right now. And this is going to overshoot. It's going to be 1 more than the number of zeros. So then I go ahead and update it like this. Super hacky stuff. I wonder why I'm doing it like this. I should be doing it with minus minus. Is it valid? No. So that's why I don't do it. Okay, so these overshoots, that's all right. And then I fix it. And then this line is the one that I'm thinking about right now. Well, this is actually a fixed number. It is $32. Yes, 32. And I think it is incorrect. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, it sounded like it was more like 16. And that, I think, concludes the logic. So it goes from 0. Let's see how many characters we have here. We have 16 characters, and then it wraps around back to 0. There may be a off by 1 mistake here somewhere. But I'm confident that this is going to have... It's going to make some noise. Hopefully. We'll see. We'll see if it makes a noise. Let's save this one and full compile reset that one. And there is a syntax error in line 621. Was it expecting parentheses? And it blows up. All of that just to blow up. Yeah, blowing up. Okay, so let's review the logic for this, but actually let's commit what we have because we did a lot. If we got this wrong, it wouldn't do any harm. It just would not update as many of the pink noises as it should. So maybe the issue is here. Well, if we don't do this loop, then it should be producing white noise because it is not going to update all the different lines. It's always going to be updating line 0. So let's try this. It's blowing up. If I don't update the previous output, it is 0. So that should be producing white noise by the virtue of this part. That is producing white noise. Great. So let's work our way back. If this occurs, that's no big deal because it's not really used. But that blows up. And it's absolutely super slow. That is interesting. What's happening with all these local variables? I cannot really interact into them, but I see my computer starting to be unhappy with this. So maybe this logic for counting zeros is not good. I don't know. But this is it. Tomorrow I'll be back here and I will figure this out. But for now, I'm going to sign off. Thank you all for being here. Thanks for subscribing to the channel, supporting me on Patreon, participating on the chat, doing all the good stuff that you do. Tomorrow I will be back here and we will figure out what the heck is going on. Maybe there is a performance issue that maybe all of this bit twiddling is not making my computer happy. Not sure why. This was supposed to be relatively easy for the computer to do. And even if I don't update the previous output, it still blows up. So it's not a good way to live. Yeah, we'll figure it out tomorrow. I see you back here at 6:30 UTC. Bye. Have a good one.